In this video, we are going to discuss the substitution rule for evaluating integrals. Our learning objectives are fairly straightforward. Evaluate indefinite integrals, evaluate definite integrals using substitution, and we'll also look at one example of how you can use symmetry to evaluate definite integrals. Basically, here's the idea. We don't have formulas for this type of an integral. We have pieces for just a plain power rule. We have pieces that are trig functions. We have a lot of formulas. But we don't have a chain rule for integrals. You'll note each of these functions are based off the idea of a chain rule. Remember, if you're taking the chain rule was used to say, take the derivative of a function inside a function. Well, how do you work backwards through chain rule? That's the idea that we've got going on here. We're looking at this and saying, here is a function of 1 minus 2x inside a function of x to the 9th power. Well, how do you integrate functions inside of functions? That's the basic idea. The answer is actually going to be a change of variables. If we can rewrite it with a different letter, a different variable, and put it in a format that we do know how to use, we can then do the conversion, do the integration, and then convert backward. Here's our first example. Evaluate the indefinite integral by making the given substitution. Please notice this is sine of pi x, so we have the function pi times x inside our function of sine. Well, we know how to do an integral for something just of sine of theta d theta. If it were just a plain sine, we know that the antiderivative of sine is negative cosine of theta, plus a constant. But this is heavily based on the idea that it's just a plain variable. We don't have that. That's where this technique of u-substitution is going to come into play. Let u be equal to pi x. That way it's going to be just sine of u. Sine of pi x is sine of u. But here's the problem. This dx is still talking about the change in x. Our variable here is needed for the change in u. We need to change dx into a form so that it's going to say du instead. This is where implicit differentiation and our differentials are coming into play. If we have u equals pi x, if we take the derivative of this with respect to x, we get du dx. And what's the derivative of pi x? Just pi. From here, we could then do some work with our differentials, multiply by dx, which gives us du equals pi times dx. But in our original problem, we did not have pi times dx, we had just dx. So we could then say times 1 over pi, canceling it out, which then gives us 1 over pi du is equal to dx. You see how it's based on here, we're doing implicit differentiation with the blue. And then with the yellow, we were doing some work based on differentials. But where this plays a role for us now is we can make the substitution. We already substituted pi x is u, but now we know dx is 1 over pi du. That allows us to factor out the constant 1 over pi, and then we are left with the integral sine of u du. And that's exactly what we know how to do. We have a formula for the sine of u. That antiderivative we had said is the cosine, the negative cosine of u plus a constant. To completely finish the problem, we now need to convert backward. We don't want the answer in terms of u. The original problem used x as a variable, so we want to change it back into the variable x. Very quickly, we'd have negative 1 over pi times the cosine, and u is just pi x, and therefore we are completely done. This technique of changing the variable from an x into a variable u is very cleverly named u-substitution, because we're substituting in the variable u. Okay, let's run through another one. Evaluate the indefinite integral by making the given substitution. Now, we can see here we're going to wind up with a square root. Since we're taking x cubed plus 1 to be our u, this piece then is the square root of u. And we can see we have some extra pieces here. We have an extra x squared, we have the extra dx. We need all of this in terms of a single variable, which is why we will now employ implicit differentiation. Take the derivative of u with respect to x on both sides. That will give us du dx equals, and what is the derivative of x cubed plus 1? 3x squared. We can note here, of course, that simply multiplying by the dx, we would have du equals 3x squared dx. Do we have the full 3x squared dx in our original problem? No. We have this x squared, so that's good. We have this dx, and so we have those pieces, but we do not have the 3. That means we don't want to substitute in the 3. Yeah, if we just divided it over, then we'd get 1/3 du. All the stuff that we have in the problem, we have written over here on the right. That way we can substitute all of that in. This lets us know then that the x squared dx is now 1/3 du. And we'll just factor out that constant of 1/3 from our integral. The square root of u is, of course, u to the 1/2 power. And we know how to take the antiderivative of a variable to an exponent. We could employ our formula. And of course, I'm writing it with an x here, but in the actual problem, that's going to be a u. Or we could just think through it logically. However you choose to get our antiderivative, we would obtain it is 2u to the 3/2. Let me think. Yeah, 1 over 1/2 plus 1. 1/2 plus 1 is 3/2. The reciprocal of 3/2 is then 2/3. U to the 3/2. So from the work in yellow, we'd get 1/3 times 2/3 u to the 3/2 plus a constant. But one piece that I've been a little bit sloppy with on purpose, when I had factored out the 1/3, officially it should be 1/3 times the whole piece. And then we'd have to distribute across to get 2/9 u to the 3/2. And then we'd have 1/3 times a constant. So that would be c over 3. Nobody writes c over 3 though, because remember, c can be any constant. So a constant divided by 3 is just some other different constant. So there's no point in writing c over 3. We would just say it's some other different constant. So people generally don't write this big step with the parentheses. That's for the main reason. This is one of the big reasons why when you're doing your work, most of the time people don't bother writing the plus c until the very, 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 very end. Yes, it should be included, but because we know it doesn't have any effect until the very, very, very end, we kind of just say we don't care. Okay, what about this one? A little bit tougher in that we're not told what the substitution is. So you have to inspect this and come up with your own substitution. When you look at it, what do you think you should substitute? What should you look for to try to figure out what you're going to substitute? Well, our last two actually give us some clues. The original problem we had, sine of pi x. You notice how pi x was the function inside the outer function of sine? We took our substitution to be the inside function. Same thing when we looked at this. X cubed plus 1 is the inside function for the square root. Square root's the outer function. And so we did our substitution to be the inside function. That's what you're going to search for. Your first intuition on this should always see, do you see a function inside another one? Well, we should be able to see the 1 over x inside the secant squared function. And so we could take the guess 1 over x. Now, of course, we know secant is also an inside function inside a squared function. So why aren't we saying let u be secant of x? Mostly because we have a formula for secant squared. We know what the antiderivative of secant squared is. We had a formula for that. So since u is equal to 1 over x, of course that's x to the negative 1. Taking the derivative, du dx, negative 1 x to the negative 2. And that then tells us du is equal to negative 1 over x squared dx. In looking at this problem, I had the suspicion that I copied the problem incorrectly, and my students have verified from our notes. When we make this particular substitution, you see how we have the over x squared? But in the original problem, we had just over a single x. That would be a problem because they don't match up. It would actually be a very, very big problem. And when I noticed that this was going to happen, I asked the class and they told me, yes, I copied the problem incorrectly into my notes for this. This problem was supposed to be x squared, and I just copied the problem down the wrong way. Fixing my error in copying it, we can now continue this though, because we can see we have 1 over x squared with 1 over x squared dx being dx. What's the only thing that we need to move over? The negative. This would be a negative du, which allows us to then make the substitution that this is a negative factored out, and we'd have secant squared u du. From here, let's use our formulas. What is the antiderivative of secant squared? The integral or antiderivative for secant squared is just tangent. And because we had the negative here on the outside, we'll wind up with the negative there on the outside also. We need to then plug back in our u. U is equal to 1 over x. And we have our antiderivative. Evaluating the indefinite integral, we're finished. All right, with our next example, what do you suspect we should use for the u substitution? Let u equal, I'm being told x cubed, because x cubed is inside the cosine. That'll tell us du dx equals 3x squared. And so du is 3x squared dx, which is a good thing because we have x squared dx, but we don't have this 3. So 1/3 du equals the x squared dx. And it's the x squared dx that we're going to substitute in. Making our two substitutions of u and 1/3 du, those two pieces get plugged in, so we'd have 1/3 cosine of u du, and the antiderivative for cosine is sine. But then we know, substituting back in, u is equal to x cubed. And so we're done. We have our antiderivative. In each of the examples we've looked at thus far, we've always had indefinite integrals, where we did not have vertical lines for the bounds. If you change it to a definite integral, how does that change things? Most of the work is going to be the same. You will still set up your u substitution. This one looks like we should have u be equal to pi t over 2, or pi over 2 times t. That would then give us du dx is just pi over 2. I said dx. It's based on t. I got to backtrack a little bit, guys. I just wrote dx here, du dx. We're taking du dt, the derivative with respect to t. I was misspeaking. Anyhow, to continue it, we would then get du equals pi over 2 times dt. But we don't have a constant of pi over 2 over here in our integral. So we could multiply by the reciprocal, setting up the constant 2 over pi times du equals dt. And that will allow us to make the substitution. Cosine of u du with the constant 2 over pi factored out. So far, all the things that I was writing are the exact same thing as the indefinite integral. Here is a common error students will make, and it's an error you must avoid. It's very common that students will incorrectly say, let's go from 0 to 1. Why is that wrong? These bounds for 0 and 1 are based on having the t value starting at 0 and the t value going up to 1. Well, if t is starting at 0, does that guarantee you that u starts at 0? No. If t starts at 1, does that guarantee you that u goes up to 1? No. When we are putting in these bounds for 0 and 1, we have to actually change the bounds into the u variable also. That's done right here. If we were to say t is equal to 0, which was our lower bound, what's the value for u? Also 0. So for that one, there would have been no problem. But if we came back and said t is equal to 1, u has to go up to pi over 2, and so it changes the upper bound for this particular problem. Now, if we wanted to, we could have ignored the 0 and 1 completely and done our indefinite antiderivative and then changed it back into t. At that point, when it's changed back into the variable t, we could have used 0 and 1. My preference, though, let's just change it right away off the bat, that we don't have to worry about at the end potentially forgetting to do it. Just remember it at the beginning. So, what is the antiderivative for cosine? Negative sine of u, and the u variable is being evaluated from 0 to pi over 2. Yes, positive sign, thank you. This would be a positive sign, not a negative sign. And so we then have 2 over pi, the sine of pi over 2, subtract the sine of 0, which is 2 over pi. The sine of pi over 2 is 1. Sine of 0 is 0. And therefore, we wind up with the overall answer, 2 over pi. And we're done. Please notice, when we were doing this here in the black, we did not need to change it back into the variable t. Because it was an indefinite integral, we did not need to change it back. I mentioned if you wanted to, you could. At this stage, we could have instead written it as sine of, instead of saying u, we could have changed it back into pi over 2 times t. But then it would have been evaluated from the t value of 0 up to 1. And you'll note that would have been 2 over pi. Sine of pi over 2 times 1 is pi over 2. Pi over 2 times 0 is just 0. And you see how you get the exact same step? Basically, whether you choose to change it back into the variable t and evaluate it from 0 to 1, well, that's doing it toward the end. My preference is just to do it back at the beginning. In my brain, it's just, that's the wiring of my brain says that's easier. If you prefer the second method, you of course can do it that way. I just think doing the first way is easier, so I will do this way on the board in the black instead of this method in the yellow. Okay, let's evaluate the definite integral. What substitution should we make? U is equal to t over 4, which tells us du dt is 1/4. That would tell us 4 times du is equal to dt. And we would also know at the same time, if started writing u, I wanted to write a t. If we have t equals 0 for the lower bound, that tells us u is also going to be a 0. But if we use t equals pi, u is going to be equal to pi over 4. Okay, making these substitutions, the lower bound of 0 for t is a lower bound of 0 for u. The upper bound of pi for t corresponded to an upper value of pi over 4 for u. And then we had secant squared u du with the 4 factored out. Did all of that make sense? Okay, I'm seeing heads nodding yes, so let's evaluate what is the antiderivative of secant squared? Tangent. And u is going to be evaluated from 0 up to pi over 4. Therefore, we'd have the tangent of pi over 4. Tangent of pi over 4 is 1. The tangent of 0 is 0. Therefore, we wind up with a final answer of 4. And we're done. Okay, let's consider this integral. What type of substitution do you think you would like to try? And I'm getting a lot of crickets. People are staring at it and saying, okay, I don't see it. What am I going to do? I don't see it. One of the big parts, remember, about u-substitution, u-substitution is helpful if you have a function inside a function. That is, we have a composition of functions. This does not have a composition of functions. Okay? We won't be able to factor out x to the fourth because x to the fourth is it's a variable, it's a function. We can only factor out constants. At the same time, we also won't be able to go through and say, let's split this up. Another intuition students sometimes try to do is say, let's split this up and multiply the two. Unfortunately, that does not work either for the same reasons that, remember when we were doing the chain rule and we said, or when we were checking out the product rule, and we said, let's just take the two derivatives and put them together. The same way that the product rule derivative failed, this fails similarly. It just, if you wind up doing some inspection, you wind up seeing that this just fails very quickly. Anyhow, the point that I'm going to note is actually based on an observation of something like this. Do you notice that the bounds are the same except for being opposites? Well, let's say I have a graph that I'm just going to say, different example from the problem, this is -2, this is +2. And we set it up here and saying this is our line y equals x. What is the area from -2 to +2 for just the simple function y equals x dx? Well, please remember, if you have area that is underneath the x-axis, it's considered negative area. Well, my drawing is crap, but we would know that this is actually the same triangle above and below the x-axis, so these areas are going to wipe each other out and be 0. If you have an odd function, you will wind up with the rotational symmetry that will take this piece, rotate it down underneath the axis, and then the areas will wipe each other out. This is a strategy that, depending on if you recognize it, depending on the type of function you have, can actually be very, very beneficial. Specifically, it's beneficial here because x to the fourth is an even function. Sine of x is an odd function. And we had already discussed at the beginning of the year, if you have an even function times an odd function, the overall result is going to be an odd function. This is a piece that we would need to recognize as being odd. Okay, odd functions have rotational symmetry. Even functions have y-axis symmetry, where you can flip it. In particular, to help visualize this a little bit, I put together the graph. Here's our graph from close to negative pi over 3 to positive pi over 3, and we're looking at it and saying, what is the combined area for these regions, for this region? Because it has rotational symmetry, this area is negative, this area is positive. The overall answer is just 0. And we don't need to know anything about what the antiderivative is. We don't need the fundamental theorem of calculus to get the antiderivative. We just know the areas are going to wipe each other out because it's an odd function. Overall, please remember the criteria for an odd function. If you replace it with negative x, you get the opposite factored outward. This was the criteria to be an odd function. Anything that fits this criteria in the blue, as long as you make sure the bounds are balanced on the left and the right-hand side, you get the exact same area for the exact same spot, and they will wipe each other out. That finishes off our 3 learning objectives. Can you use u-substitution to evaluate the indefinite integral, where you have to put on plus a constant? Can you use u-substitution so that you can change the upper and lower bounds and then use the fundamental theorem of calculus to evaluate the definite integral? And would you be able to recognize an odd function that will wipe out the area just being overall 0? If you can do those 3 things, then you've met our objectives for today.